5.2, solving systems of linear equations by substitution. We've got three methods for solving a system. A system, again, is two linear equations together on the same graph, working together, being compared. When we're solving that system, we're looking for the point where the two lines intersect, the point that works in both equations. So in section 5.1, we looked at how we could use graphing to solve a system. And now here in 5.2, we're going to look at the method of substitution. Later in 5.3, we will look at the addition method of how to solve the system. Just as a note on exams, it'll be your choice of method. You can choose your favorite, or you can choose based on what the problem kind of lends itself best to. If it's easier to graph, easier to use substitution, easier to use addition, or again, you can choose the one that you prefer. But for now, in the textbook sections, go ahead and use the method that they suggest. In this case, we're going to practice the substitution method. And if the instructions also say if there's no solution or an infinite number of solutions, so state. Recall from our last section that no solution occurs when the two lines are parallel, and an infinite number of solutions occurs when the two lines are the exact same line, right on top of each other, and so all points on that line would work in both equations, and lines go on forever, and so that's why there's an infinite number. The other thing that the instructions say is that we're going to use set notation to express our solution sets. So that's again with the braces around our coordinate point. First example, number 4 from page 307. The two equations are 2x minus 3y equals negative 13. And this is in standard form. Second equation is y equals 2x plus 7, and it's in slope-intercept form. And let's look at the steps of how we would solve a system using substitution. Then we'll apply each of those steps as we go through this example. First step, we're going to solve one of the equations for one of the variables. In this case, equation 2 down here at the bottom is already solved for y, so step 1 is already taken care of and done for us. The second step would then to be substitute into the other equation. That's the name of this method, substitution. Substitute in the other equation. What would that look like? Well, in the first equation here, we'd go ahead and rewrite it. 2x minus 3, instead of the y, we'd leave some space because we're going to replace it with what the other equation is solved for y, equals negative 13. And we would take what the second equation says, y equals, and replace y in the first equation. And that is step 2. Done. Step 3 then is to take our new equation and solve for the one variable that's left. Which will give us half of our answer. In this case, we're going to solve for x, and it'll tell us the x-coordinate of the point that is the solution to this system. When we solve, we'll start by distributing the negative 3 here. We get 2x, negative 3 times 2x is negative 6x, negative 3 times positive 7 is negative 21, equal to negative 13. From there, combine like terms, 2x minus 6x is negative 4x, minus 21 equals negative 13. Add 21 to both sides, and you get negative 4x is equal to positive 8. Divide both sides by negative 4, and I get x is equal to negative 2. So that entire solving process was our step 3 as we were solving for one of the variables. Now we know one piece of the point that is the solution to this system, the point that works in both equations, the point where these two lines cross on the graph. But we need our y-coordinate to complete this. So the fourth step then is to plug in and solve for the other variable. Plug in and solve for the other variable. It doesn't matter which equation you use. You can plug that into either equation. This is known as back substitution. You're taking your answer, plugging it back into the original to find the second part of the solution. So in this case, I'm going to go ahead and choose to use equation 2 because it's already solved for y, and I can take our x and plug into it. Okay, and that was my choice there. I could have used equation 1 and it would have worked out just fine. Equation 2 just lends itself a little easier here. So y equals 2 times x plus 7 instead of x. I leave some workspace to plug in our value of -2. Solving from there, I get 2 times -2 is -4 plus 7, and that's going to equal a +3. And we're going to use set notation to display our answer here, but before we do that, let's go ahead and do step 5, which is to check our answer. Many times you can do this mentally in your head, but check the answer in both equations. It needs to work in both. And this right here is step 4. And then step 5, -2, 3, checking it in both here. 2 times -2 is -4. Minus 3 times 3 is -9. -4 minus 9 is -13. So it does check. Okay, and then in equation 2, put a -2 for x. Should get a 3 over here for y. 2 times -2 is -4 plus 7. That does give you a value of 3. So -2, 3 does check in the two equations, which means we can move on to writing it in set notation, which is where you take the fringe. They're not really fringe, they just seem extra fancy here, the little braces. You put the coordinate point in parentheses because order matters. You just show that it is a point on the graph, -2, 3.